morning, students. Myself, Vijay Shankar from EC Department, Civil Engineering College. Today, we are going to discuss about another topic in the third unit of electrostatics. In the previous class, we completed the potential difference and work done and the potential difference. Now, we go for the discussion about the potential difference due to the line charge, potential difference due to the surface charge, potential due to the volume charge. Okay, my dear students. So, potential due to the line charge. See, what is the potential due to the point charge? Potential due to the point charge, V is equal to Q by 4 pi epsilon naught R. Okay, and if having the another charge is also there, that is a V is equal to Q by 4 pi. Hence, when from the origin to the point A, and the charge that 4 pi epsilon naught into R minus R dash. If several number of charges are there, that is a sum of I is equal to 1 to M R minus Ri and the Qi also. Okay. Now the differential voltage dV is equal to the same equation. Now I'm writing the dV is equal to change of the charge dQ by 4 pi epsilon naught into R minus R dash. So what is a dQ? When the potential due to the line charge, we already know the change of charge with respect to the length dl is equal to charge density rho L. So dQ is equal to rho L into dl. You can see here, considered a line charge having the density. It is a line charge diagram. Density is the rho L, as shown in the figure here. Consider a differential length dl bar. See here, the differential length dl bar is a point at a distance r. At a distance r dash, it is from the origin. It's r dash from the origin. Then the differential charge on the length dl bar is given by the dq is equal to rho L into dl of. Since it is a distance of r dash, you get the rho L of r dash. So no need to represent the rho L of r dash. So directly can write the dq is equal to rho L into dl. So rho L is a line charge density at r dash. So they are representing the rho L of r dash. Let the potential A is determined, then the differential voltage or the differential potential change of the potential is equal to dq by the 4 pi epsilon naught r minus r dash. This r is a distance from origin to the point A, and the r dash is the distance from the origin to the differential length what we are assuming on the line, a small differential length. So this is r, the capital R. The capital R distance is r minus the r dash, indicates the distance of point A from the differential charge. Got it, my dear friends? So that equation here, the change of the voltage is the change of the charge at dq. Now representing both sides the integral value. It becomes of VA. The voltage at the point A is equal to VR means the distance from the origin to the point A is R, so they are representing V of R is equal to the line integral dq by 4 pi R only. Okay, that R is nothing but R minus R dash. Small r minus small r dash. Small r is the distance from origin to the point A, and R dash is the distance from origin to the differential length dl bar. Okay, the VA is equal to, what is the dq? We got the rho L dl. So the rho L of R dash dl bar. So they are assuming the dl bar 4 pi epsilon naught r, the integral of the line integral VA is equal to, and the V is equal to, simply V is equal to the line integral rho L dl by 4 pi epsilon naught into R. Okay, into R. These are volts in terms of volts. Or otherwise, we can represent the V is equal to the line integral of rho L dl by 4 pi epsilon naught. What is R here? In terms of the distance from the G origin to the dl bar and the origin to the point P is R minus R dash. The voltage, the potential due to the line charge. Okay. Potential due to the line charge. So next we can see the potential due to surface charge. Potential due to the surface charge. Here, previously we considered a line with a charge of rho L is a charge density, a small differential length we assume on that line, taking the distance from origin to that point and origin to the point A. Now, considered a surface with the uniform charge density rho S, a small differential surface at the point P. So consider the uniform charge density rho S, consider a differential surface area ds at point P, where the rho S is indicated as rho S R dash, or you can simply the rho S only, no need of R dash, because R dash is the distance. Okay, simple, it is a rho S. What is the change of dq by ds is equal to rho S? The charge density is a ratio of change of charge with respect to the surface is a rho S. dq is equal to rho S into ds. Rho S into ds. Now, what is the voltage at the point charge? P is equal to the potential at the potential due to a point charge is a q by 4 pi epsilon naught R, actually R. Now the differential voltage or the differential potential dV, the change of potential is a change of the charge dq by 4 pi epsilon naught R. 4 pi epsilon naught R. Now the substitute the dq is equal to rho S to ds. So dV is equal to rho S into ds, all divided by 4 pi epsilon naught R. And now apply the integral on both sides. So V is equal to the volume, not the volume integral, surface integral rho S ds by 4 pi epsilon naught R. 4 pi epsilon naught R. The volume differential surface integral here. Okay. So say the VA is equal to rho S ds by 4 pi epsilon naught R. This R dash is a rho S. No need to represent the rho S of R dash like this. It's a uniform charge density rho S of R dash is equal to rho S of. Got it? is a potential due to the surface charge. A potential due to the volume charge. The only difference here also we consider as a line is converted to the surface and surface is converted now the volume. The total volume, the dV, the point P, and the charge is uniformly distributed. The charge density is a rho. Consider a uniform volume charge density rho V over the given volume as shown in the figure. Consider the differential volume PV. Consider the differential volume PV at a point P where the charge density is a rho. Charge density is a rho. So dQ by dV is equal to rho V. dQ by dV is equal to rho V, and the dQ is equal to rho V into dV. Rho V into dV. So what is the volume potential due to the point charge B is equal to Q by 4 pi epsilon naught R. 4 pi epsilon naught R is a formula, my dear students. We already proved that it is a potential due to the point charge. So change of the potential, the dV is equal to dQ by 4 pi epsilon naught R. What is the dQ? Rho V into dV. Substitute there. dV is equal to rho V into dV whole divided by 4 pi epsilon naught R. 4 pi epsilon naught R. Now apply the integral on both sides. V is equal to the volume integral now. The volume integral rho V dV by 4 pi epsilon naught R. 4 pi epsilon naught R. Okay. You see, note that the uniform volume charge density rho V of R dash is equal to rho V only. Same. So finally, you can conclude the potential. These are the potential values we derived the yesterday class and the today's class. The potential difference V is equal to minus integral B to A E bar dot D bar. B is the initial value and A is the final value. And absolute potential due to the point charge. Absolute potential due to the point charge is a potential difference. The formula is there, minus integral E bar dot DL bar. Okay. And absolute potential V is equal to Q by 4 pi epsilon naught R is the volts, my dear students. V is here, the volts. Okay. Absolute potential to the line charge. Now you derive this expression, the V is equal to line integral rho L DL by 4 pi epsilon naught into R. It is the volts. Absolute potential due to the surface charge. This surface integral rho S ds by 4 pi epsilon naught R. It is also the volts. Okay. V is equal to, and here it is also the V is equal to, and this also V is equal to. Is a potential difference. Actually, the E bar is equal. How we got this expression means the E bar is the point charge is a Q by 4 pi epsilon naught R. Okay, that is the integral is a R square is there. After substituting the values in this, DL is equal to DR into AR. From that, we derive the expression of the absolute potential due to the point charge Q by 4 pi epsilon naught R. And volume is also the same. By substituting the dq is equal to rho v into d. Okay. And all the expressions R is the distance of a point A from the charge Q or differential charge D. R is the distance from the distance of a point A from the charge Q. Got it? Suppose if I am assuming that Q here and the point A is a final value and the point B is the initial value, and move the test charge QT from B to A against the direction of the electric field intensity E bar, there is a repulsion is that the force is exerted. Okay, nothing but is a work done. Work done per unit charge is nothing but the potential. V is equal to work done per the potential. W is equal to. Actually, the W is equal to minus Q, the integral B to A, or initial value to the final value, E bar dot DL bar. Work done per unit charge is a potential. W by Q is equal to minus integral E bar dot DL bar. Okay. Is applied force here. Applied force from point B to the point A. So the distance here. The distance R is the distance of point A from the charge Q or differential charge D. Got it, my students? Next, we go for the another topic. Potential difference due to the infinite line charge. Potential due to the infinite line charge. Before that, what is the potential due to the, not the potential, electric field intensity due to the infinite line charge. Electric field intensity due to the infinite line charge is E bar is equal to rho L by the 2 pi epsilon naught R into A R bar. We already derived this expression, the one of the application here. Consider the infinite line charge along the z-axis having the uniform line, of charge density rho L. The point P is at the radial distance RP, while the point A is at the radial distance of RA. See, from point B to the point A is required to move the charge here. The E bar to the infinite line charge along the z-axis also and is known and is given by the E bar is equal to rho L by the 2 pi epsilon naught R into A R. We already derived this expression, my dear students. E bar is equal to rho L by the 2 pi epsilon naught R into A R. So DL is equal, because the E bar is in the R direction, you can take the differential length DL bar is equal to DR into AR bar. As you can assume, it is a cylindrical coordinate system having the Z axis, R and the phi also. So it is R, the need of taking the A phi and the AZ because it's a zeros, the dot product. Substitute these two functions in the potential V is equal to minus integral B to A E bar dot DL. What is the E in the infinite line charge here? The rho L by the 2 pi epsilon naught R, AR bar dot DL bar is a DR into AR bar. AR bar dot AR bar is equal to 1. The integral RB, the point B, the distance is RB, and at the point A, the distance to the origin is RA. Rho L by the 2 pi epsilon naught, it becomes minus integral RA, not the RA, RB to the RA, rho L by 2 pi epsilon naught R into DR. Got it, participants? So rho L by the 2 pi epsilon naught is a constant, 1 by R is there. 1 by R means ln of R. So minus rho L by the 2 pi epsilon naught is a constant. The integral of RB to the RA is 1 by R into dr. 1 by R into dr. The 1 by R is the ln of x. So that is equal to minus rho L by, you can see here, ln of R, RA minus RB, RA minus RB. So minus rho L by the 2 pi epsilon naught ln of upper limit is RA minus lower limit ln of RB. Or otherwise, you can write this function RA by the RB ln of, here the minus is there, so RB by RE. So multiply this minus negative sign, then it becomes of rho L 2 pi epsilon naught into ln of RB minus ln of RE. Got it, my students? You can also written this as RB by RE. So V is equal to rho L by the 2 pi epsilon naught ln of RB by RE. It's the volts. These are standard result and may be used to find the potential difference between the points due to the infinite line charge. Due to the infinite line charge. The result can be used for any zero reference as a potential difference calculated does not depends on the reference. Forget about this. Up to this, you can write this. This is a standard result and may be used to find the potential difference between the points due to the infinite line. Okay, my dear friends. Gradient. Potential gradient. It is also, you can derive by using the potential equation minus integral of E bar dot dl bar, that V is at the point charge Q by 4 pi epsilon naught R. Q by 4 pi epsilon naught R is considered an electric field E bar due to the positive charge placed at an origin of a sphere. Then V is equal to minus integral E bar dot dl bar or Q by 4 pi epsilon naught R. It's a point charge. The potential decreases as the distance of point from the charge is increases. See here, again I'm saying the potential is decreases, the V is decreases as the distance of point from the charge is increases. Okay, there is no any potential when we are getting the potential, when we are there, get the work done there is any neither of the charges. There is a work done and there is a potential is developed. Here, the potential is decreases as the distance of point from the charge is increases. The R, whatever the R is there, that is a distance. It is known that the line integral of E bar between the 2 points is given as used as a potential difference between the 2 points for the elementary length delta L. So A and the B is a differential or the small incremental length, you can say. Delta means it is an incremental length or elementary length, delta L. Here there is a y-axis, the delta B. So VAB is equal to delta B. Incremental potential delta B is equal to minus E bar dot DL I consider as a delta V. Otherwise, the V is equal to integral E bar dot DL bar. Take the derivative on both sides. So dV is equal to E bar dot DL bar. Is it right, my students? The derivative of integral is nothing but the constant E bar dot DL bar. Now I take this change of the potential is a small incremental volume, not the volume, incremental potential. Delta V is equal to minus, already the minus is there, minus E bar dot length, also the elementary length DL bar. Okay, delta V is equal to minus E bar dot D delta L bar. Hence, an inverse relation, namely the change of the potential delta V along the elementary length delta L must be related to E bar as delta L tends to the 0. As delta tends to the 0. So the rate of change of the potential with respect to the distance, the rate of change of the potential means the rate of change of potential dV with respect to the distance dl is called the potential gradient. As we can write this, the change of the potential with respect to the distance dl or with respect to the length. In terms of the elementary length, limit delta L tends to 0, delta V by the delta L is equal to the gradient or the potential gradient. Got it, Martin? Potential gradient is nothing but the slope of a graph of potential against the distance at a point where elementary length is considered. Okay, as the potential is decreases, as the distance is increases. So dV by dl is equal to or limit delta L tends to 0, delta V by delta L is equal to the potential gradient. And now the relation between the E bar and the P, consider E bar due to a particular charge distribution in the space. The electric field E bar and the potential V is changing from point to point in a space. Consider a vector incremental length delta L bar making an angle theta. See here, making an angle theta with respect to the direction of the E bar. To find the incremental potential, we use the formula we already know, the delta V is equal to minus E bar dot dl bar. What is the delta L bar is along the direction of the AL bar. So delta L is equal to delta L, and the delta L bar is delta L into L bar. L bar is a unit vector. Now the dot product E bar dot delta L bar is equal to. So E is in the L direction, EL into AL bar dot delta L into L bar. So component the direction. So E bar dot DL bar is the product of components E bar in the direction of AL bar. So E bar dot delta L bar is equal to EL into delta L. So AL bar dot AL bar is equal to 1 ohm. Got it, participants? And delta V is equal to minus EL delta L minus EL into delta L, where the EL is a component of E bar in the direction of AL. So when the theta, the dot product we can consider delta V is equal to E bar dot DL bar. E bar is a magnitude is a E and delta L bar is a magnitude is delta L and the cos theta, the dot product. Okay. We know the dot product of E bar dot delta L bar. That's the thing about the change of the potential of delta V is equal to, see here the V is equal to minus the integral of E bar dot DL bar. It's a formula of the potential, and dV is equal to minus E bar dot DL bar. Is a dot, my dear students. And the dV, I am taking that as a incremental potential, is a minus E bar minus dot delta L bar. Now apply the dot product here. The formula, the dot product is a magnitude minus the magnitude of E bar and magnitude of delta L bar and cos theta and cos theta. Okay, and delta V by the delta L. Now I'm taking here the delta L here, minus V into cos theta. Minus V into cos theta. To find the delta V at a point, check the limit delta L tends to the 0. Okay, limit delta L tends to 0 on both sides. So in the right hand side, there is no any delta L. So no need of representing of a delta, limit delta L tends to 0. So what is the limit delta L tends to 0 or delta V by delta L is nothing but potential gradient. Okay, but the limit delta L tends to 0, delta V by delta L is equal to dV by dL, or it is also called as a potential gradient. So now that dV by dL, whatever we have, the dV by dL is equal to minus E into cos theta. Minus dV by dL is equal to minus E cos theta. Okay. At the point P where the delta L is considered, E bar has a fixed value. E bar has a fixed value while delta is also constant. Hence, the potential gradient dV by dL can be maximum only when cos theta is equal to minus 1. Got it, my dear students? At point P where the delta L is considered, in the diagram here, at point P, wherever you can find the potential gradient, at a point P where the delta L is considered, E bar has a fixed value and the delta L is also a constant. Hence the potential gradient dV by dL can be maximum only when cos theta is equal to minus 1. Means theta is 180 degrees. This indicates that delta L must be in the direction of opposite to the E bar. So dV by dL at the maximum is equal to E. What is a cos theta here? Cos theta is 180 degrees. Cos theta is a minus 1. Minus into minus becomes a plus and E on. This equation shows that the maximum value of potential gradient gives the magnitude of electric field intensity E bar. Okay. The maximum value of rate of change of potential with the distance, the potential gradient is possible only when the direction of increment in the distance is opposite to the direction of E bar. Opposite to the direction of E bar. So E bar is equal to, then it becomes of E bar is equal to. Now I'm taking this vector in the terms of direction, E bar is equal to opposite direction. So negative sign indicates opposite direction dV by dL at the maximum. And whenever I'm taking it is a scalar quantity here, when I'm the vector quantity, the direction is also can represent K and bar. The negative sign is the maximum value of rate of change of potential with the distance, that is potential gradient is possible. Potential gradient is possible only when the direction of increment in distance is opposite to the direction of E bar. So that negative sign will get. Thus, if A n bar is a unit vector in the direction of increasing the potential normal to the equipotential surface, the E bar can be expressed as minus dV by dL. Minus dV by dL. Okay. And the maximum value of rate of change of potential with the distance dV by dL is called the gradient of V. Gradient of V. The mathematical operation of operation on P by which minus E bar is obtained is called a gradient, or it is denoted as gradient of V or grade V or del V. The maximum, the rate of change of See, the maximum value of rate of change of potential with the distance dV by dl is called gradient of V. Gradient of V means E bar is equal to this minus grade V or gradient of V. Gradient of V or del V. Del V means E bar is equal to minus del V. It's a gradient of V. It's a del V. E bar is equal to minus del V. Got it, my students? So mathematical operation on P by which minus E bar is obtained is called gradient and denoted as gradient of V or grade V or del V. So del V is equal to grade V, that is equal to minus E bar, or E bar is equal to minus del V or minus grade V. Got it, my students? Now, the del operation for the, in the space, the potential is unique. The function of x, y, and z coordinate in this Cartesian coordinate system. dV is equal to rho v by, not the rho v, partial differentiation, dou v by dou x dx, dou v by dou y into dy, and dou v by dou z into dz. Okay. In Cartesian coordinate system, coordinates E bar is equal to Ex, Ax, Ey, Ay, and Ez, Az bar. And dl is a dx, dy, and dz. We already know, my dear students. By taking the potential formula, the dV is equal to minus E bar dot dl bar. E bar is Ex, and dl is equal to dx into something. So Ex into dx plus Ey into dy plus Ez into Ez, because Ax bar dot only, it is a 1. The remaining is a zeros. Ay and Ay dot is only 1. So the magnitudes are product Ey and dy. Now, where comparing these two functions, dV is equal to rho v by rho x into dx, and here Ex is the coefficient of dx and the rho v by dou v by dou x is the coefficient of dx. So Ex value is minus rho dou v by dou x, and Ey is equal to minus dou v by dou y, and Ez is equal to minus dou v by dou z. Got it, my students? So E bar is equal to, substitute the Ex as this function, minus dou v by dou x into Ax, minus dou v by dou y, and dou v by dou z. And take the V as a common here. E bar is equal to minus dou by dou x of Ax bar, dou by dou y of Ay bar, and dou by dou z of Az bar into V. The total function of product of V is del. The del operator, the potential V is a scalar, but the operator on V is given, the equation is a vector and is called del operator or denoted by the del, or it calls also grade V. E bar is equal to minus del V. Del is a function for the Cartesian coordinate system. It's dou by dou x dx, dou by dou y dy, and dou by dou z of Az bar. The similar fashion for the cylindrical coordinates also, del V is equal to, see here V, there is no V, only the del function. Del V means dou V by dou x, dou V by dou y, and dou V by dou z also. Similar fashion here for the cylindrical coordinates also, del V is equal to dou V by dou r, phi, and the z is a coordinates of cylindrical. Dou V by dou r into ar bar, and dou V by dou phi, and dou V by dou z. Actually, the phi is not alone, we are getting the 1 by r is multiplied. Similarly, for the spherical coordinate system, del V is dou V by dou r into ar bar, and theta is also multiplied with r, so it is a 1 by r into ar bar, and phi is multiplied with the r sin theta. That is the inverse we will get here, 1 by r sin theta. Got it, my dear students? Actually, the differential elements is here the dx, dy, and the dz. And here the differential elements is dr and r into d phi, dz. Okay. So dr means dou v by dou r, dx means dou v by dou x. And here for d phi, 1 by r into dou v by dou phi. Remaining all is the same. And similarly for the spherical coordinate system, dr and r into d theta, and here the r sine theta d phi. Okay, so dr is dou v by dou r into r bar only, and d theta dou v by dou theta, and r is 1 by r, and r sine theta is multiplied here 1 by r sine theta. This is a gradient B or del B for Cartesian, cylindrical, and the spherical coordinate system. Got it, my dear students?